university, right?
Yes, correct. Can I also stand, or is that?
I think so, yeah.
Can I use this to do the slides? Okay, welcome all. Thank you for participating to this conference and willing to listen to my talk. Also, welcome to the people on Zoom. And thank you for the organization of the conference. I've been really enjoying it so far. Yeah, and I will talk today about natural gradient, and then in particular on the natural gradient applied in overparameterized systems. And there has been some discussion within or some confusion within the community about whether in this setting the parametrization independence of the natural gradient is maintained. So that's in a nutshell what I'm going to talk about. And hopefully to clear up this confusion. And before I'm going there, I'll first just introduce some more notation on top of all the notation you've seen so far. And I will do that in the non-overparameterized setting first, so that everything is hopefully a bit easier to understand. And after that, I will go to the overparameterized setting. I will do as much as possible with pictures, so that there's also some kind of intuitive thing, because we're doing geometry, so that's always the nice thing. Yeah, so what we are starting with is a space of parameters, which I'm calling capital Xi, and it's just an open set of RD. And then there is a parametrization map from this parameter space to a Riemannian manifold of probability distributions. And then the whole space it's mapping to, I'm calling Z, but then the image of this map I'm calling M. So I'm mainly working with M, so this Z is a bit in the background. And then on both of these spaces, we have also tangent vectors. So here it's just from the coordinates, and then these are basically mapped through this parametrization map, this map phi. And then lastly, we have a function L on this manifold, and that can be interpreted as an objective function. So for example, if you're trying to optimize a neural network or any other parameterized model, then it's also sometimes called a loss function, but I'm assuming here, then I don't have to deal with minus signs, that the higher this function, the better. So we want to go to the maximum of this function L. And then lastly, we can take the derivatives with respect to this coordinate space of this function L. So that is basically if you take the combined map all the way here, and then, so that's just the vector of, yeah, let's say partial derivative or coordinate derivatives. I'm denoting here with this NAPLA. So that is that for notation. And then for the discussion now, or most of the discussion, I will be restricting my attention to non-singular points on the manifold. And furthermore, I am using this Einstein summation convention, hopefully. That is familiar to most people. Okay, before I'm going to the natural gradient, I'll first just discuss the normal, the standard gradient that is calculated often when you're, for example, optimizing a neural network. And then in my notation, that will look like this. So we have this vector of coordinate derivatives, and these are the tangent vectors on the manifold M. And then, so what that looks like very simply is if we have this manifold of probability distribution, so in this case, the normal distributions, then we want to find the optimum of this function L on this manifold. And then at some point in the optimization process, we're, for example, here, and then we're just trying to find basically the direction of steepest ascent. And then we calculate it by just calculating this. So that is hopefully all familiar to most. Yeah. And then now I'm going to the natural gradient. So one thing that is good to say, I think, is that so in information geometry, many people refer to it as natural gradient, but if you're just coming from a background of more differential geometry, it's actually just called the Riemannian gradient of a function. So it's in that sense a little bit less special as it seems if you have only heard the term natural gradient. And yeah, so in differential geometry, the Riemannian or natural gradient is defined implicitly using the Riesz representation theorem. So if we have on this side the differential of the map L, so that's a part of the cotangent space in a point P, then we can use Riesz representation theorem to find basically the representation in the tangent space of this cotangent vector using the metric that is on the space of probability distributions. And then in the context of the natural gradient, this inner product is often the Fisher metric, given by the Fisher metric, but actually in our context, it doesn't matter which Riemannian metric you're choosing. So I'm leaving that also a bit more open. So this is how the gradient is defined. And I'm already saying here, note that that there is no reference to any parametrization here in this definition. Yeah, and then how do you then calculate the natural gradient or the Riemannian gradient? That is then given by this formula. And then here we recognize again the formula we have here, but then we are somehow rescaling this vector of coordinate derivatives by the inverse of this matrix G. And that is just that matrix G is just the metric where we plug in all the different coordinate tangent vectors that are living here on this manifold M. So yeah, so this is a short introduction to the natural gradient, how it's calculated and how it's given in this notation, and a short references of the natural gradient. So it was in 1998, it was first proposed by Amari, and in this paper here, and then it was further studied by Giovanni Pistone, and then now currently there is quite many applications. I'm here just referring to two. By the way, what's good this is not an exhaustive list at all, not an attempt to have an exhaustive list of references, but just the ones that are also a bit relevant to the current presentation. So this is some nice applications of the natural gradient within reinforcement learning and robotics. And then actually it's still a very like ongoing topic of research. So there's a nice paper of Martens. He's working at DeepMind, I think, explaining quite a long paper on all kinds of aspects. And then this is a nice paper by Bernacchia, also on for deep learning, so also the overparameterized setting. And then Nihat, my supervisor, he has a nice paper and also this paper, and they are both on how can we optimize this inversion of this matrix G we just saw here, because that is often a bit of a problem within the natural gradient. And then two papers here. So Luigi Malago and Lia Montouvar, they are both working on the natural gradient, but they're not using the Fisher metric, but actually using the Wasserstein metric. And as I already said before, the results I'm going to present now are also relevant in this setting of not using the Fisher metric. So that's a short historical overview. And then now we're going to the overparameterized setting. So the actual topic of the presentation. So yeah, so before we had that this map phi, was mapping from a d-dimensional space into a d-dimensional statistical manifold. But now we are loosening that assumption that that this map is like a local diffeomorphism, and we're only assuming that it's a smooth map. And then and this is, of course, if, for example, in the context of deep learning, that is often the case, that you have a very large parameter space, but then the actual space of distributions is way smaller. So it's quite a relevant topic, especially now, because people are trying to apply this natural gradient in this context. So yeah, and then the main problem, or the apparent problem that is then happening, is then that this matrix G here, that is calculated by plugging in all these tangent vectors from the parameter space, that will then become degenerate. So it's no longer mapping on the full d-dimensional space, but there are some directions where it's mapping to 0. And then what that means is that you can't do this. Sorry, I'm going often. So that means that you can't do this inversion anymore, because that is only possible for non-degenerate matrices. And then that is also the reason, or that is causing the some kind of confusion, because then what you can do for these degenerate matrices is to use a generalized inverse. So, for example, the MoorePenrose inverse is an inverse that is generalized inverse that is often used, and this MoorePenrose inverse that is actually calculated by looking at the whole space of possible vectors that could map to the vector that you have. So you're doing the inverse, but then the MoorePenrose inverse needs to choose one of those, and it chooses the one with the smallest Euclidean length, Euclidean distance, and this Euclidean distance is defined on the space of parameters. And then that is, so if we have that picture here, so we have some kind of thing that then depends on the Euclidean metric on this space. And then you could say, okay, but if we choose a different parametrization, then it will also automatically will give us a different vector that is the shortest vector by this Euclidean distance on the parameter space. So, and then, for example, here in this paper by Jan Olivier, he is saying it. So this is a paper from 2015. He is saying one can decide to use the MoorePenrose pseudo-inverse. However, this formally breaks the invariance properties because it chooses the one with the smallest norm. So we have all possible solutions lambda, and it chooses the one with the smallest norm, and that is not intrinsic to the manifold, basically. So this paper was actually somehow like for me the reason of writing this like my paper together with Nihat to clear up this confusion, because our main theorem of the paper is stating that it's actually the natural gradient does remain parametrization independent, right? Okay. And then yeah, so how that then, what the theorem exactly says is that we have a generalized, we give a definition of a generalized inverse, and that is just a matrix that satisfies this equation. And then our main result is just saying, okay, for any generalized inverse of G, so for example, also the MoorePenrose inverse, we can still just use the same formula as we saw earlier to calculate the gradient on the manifold. So I would say that's quite an important result, because it's somehow a little bit reassuring that you can still use the natural gradient also, for example, within deep learning or any other overparameterized setting. Yeah, and then I will just try to illustrate the result a little bit. So if we have, for example, so here we have two parameter spaces, and they are both mapping to the manifold M, and there's a diffeomorphism between the two. And then we have that F composed with phi is then this map. And then I think this is quite a nice way to show also where the confusion comes from, because if we compare, so we have we can also look at the gradient vector just on the parameter space. And then if we look at those gradient vectors just on the parameter space, there they can be different. So that is just this, basically that, this, so that will just be basically this vector that we are looking at. So that is the vector in the higher dimension. And that, oh, sorry. And they can be different. So for example, if we have a parameterization here and one here, and then we can map this one through this diffeomorphism here, then these two can be different. But then the interesting thing is when we map this to the manifold, then this whole difference cancels out. So then we just obtain this parameterization independent gradient, because then they are just the same. So that's one way of thinking about it. The other way is just what I was already mentioning earlier, that is whole gradient is the definition, like the differential geometric definition is parameterization independent. And then so the generalized inverse is only a way of obtaining this this gradient, and then it can be that it's like somehow parameterization dependent here, but when you map there, then you're all good. So I think I should probably stop here.
No,
so
2 minutes.
oh, 2 minutes more.
I have a
Then
question.
Okay.
Maybe that's also
Can we
our-
first finish and then pose the question? And just we pose one question because we are.
Okay, yeah, so then I'll just finish quickly. So there's some kind of things I would like to mention. So actually, if you're performing the natural gradient method, you're not really following the exact gradient flow. So if this would be the gradient flow like this, you're only parallel to that gradient flow at your point P. And then this gradient method is always defined in some kind of discrete time step. So you're doing a step and then a step. And then so this exact trajectory of the method can still be parameterization dependent, but that is also the case in non-overparameterized systems. So that is always some kind of issue, you could say, with the natural gradient method, but I would like to mention that just to be clear, like what is and what isn't parameterization independent. And then the same holds for, so I was restricting my attention to the non-singular points. But if we actually look at the singular point, so for example, if this is the parameter space and this is the manifold, then you could, for example, have a singularity here. And then if you perform it with one parameterization, then you get a vector here, the gradient, and if with another, you get, for example, a vector here. But the same as for the previous point, this is also a problem in non-overparameterized setting. So there is no additional problems with going to the overparameterized setting, and that's also the conclusion of the presentation. One can use any generalized inverse to calculate the natural gradient vector in a parameterization independent way. Thank you for your attention.
So I'm check if there are any questions from the audience on Zoom.
We have already a question here.
And we have a question from Rita. Please.
So first of all, I'm really glad that the community is realizing that we can't invert matrices, because I've been in this business as a geometer going around and they put the G-1 and I always said, wait a moment, I'm sure it can be inverted. So I'm glad that you stop and think about it. But I urge you not to think about G as a matrix. That's not the right way, because the right way is to think about the gradient. And that's coordinate independent.
Yeah, exactly.
And so
yeah.
if you think about the gradient with the natural metric, like a Fisher, Suppose that that is, degenerate, you restrict where it is non-degenerate. And then you have a beautiful flawless submanifold. And if this is not a submanifold, you have a sub-Riemannian flow. These things have been studied. So what I'm trying to urge you is to forget about matrices, forget about local coordinates, get the message of Cartan, Elie Cartan that said, look at the moving frame, right? That's a way to think, and not about coordinates. And then you have no problem. Okay.
Very nice.
That's what I'm urging. But I'm really happy that someone has stopped and thought, wait a moment, I'm inverting something that is invertible, yes or no?
Thank you.
And then we are, thank you again for one more question. Maybe we can do it at the end of the session.
Yeah, and if you, I will be there also in the break or later. So if you have any more questions,
That was a great talk.
Sorry, Carlos.
thank you.